Fine. Perfect. So in previous video, we talked about the noise factor, right? Which remains. So when we take a single harmonic, the first harmonic, so when we elaborate it further, so the if the input consisted of a, let's say, sinusoidal signal, so let's say the analog input is basically a sine wave. So when we convert it into a discrete domain, it would have looked like the spectrum like this, where it would have had its samples like this. But now, due to the presence of this noise, we also have the samples due to noise. So basically, when we plot them mathematically, so what we have is we have samples, right, like this, and we knew if we are sampling at a like we have a frequency fn. So after sampling, the frequency will be fn by fs times 2 pi. So then basically this value is fn by fs times 2 pi. So similarly, this value will also be like from this value. So this will also be fn by fs times 2 pi, because this noise basically corresponds to the input only. So now from origin to this point, it is pi. So then from origin to this point, so basically the location of this point will be pi minus this value. So pi minus fn by fs times 2 pi. So if we translate this continuous time, if we translate this discrete sample again back in continuous time, it's like having a tone input whose frequency is fs by 2 plus minus fn. So how it, like, you can refer to the equations, that how we got this value. So basically this will represent when we convert it to analog, so analog domain. So basically it will look like we are having a tone at the input whose frequency is this value, this quantity. So if we are unaware of the gain mismatch, then we might get misleaded by thinking that the input signal also comes with a tone whose frequency is this value. So when we are looking at the output, and if we are not aware that the output, so basically the output we need is ideal output of the spectrum, right? But we are getting this noise factor along with our output. So basically we are getting this also along with our output. So then while analyzing output, if we are unaware about the gain mismatch, then we might think that the whatever the input is, it also has a another component which is a tone of frequency of this value. So ideally, what we were expecting was, let's say, some sequence. So it was a random sequence. So this is what ideally we were expecting in discrete domain. So we had some sort of signal, any continuous signal. So we sampled it, and these were the even samples, and these were the odd samples. So it's random. Let's say we are expecting this kind of some sequence. So now, because of the gain error, every odd sample is getting multiplied by a constant. So we are getting these factors also, right? So basically, every odd factor is getting multiplied by a constant, which is occurring due to the constant gain, right? Which is 1 plus beta. And that will cause these factors, these samples. And uh, so the ideal or the expected sample is getting multiplied by these values. Same goes with the even samples. So every even sample is again getting multiplied or modulated by a constant sample. So then we saw that basically for even samples, the upper channel had the gain, which was 1 plus alpha, and the lower channel, which corresponds to what do we say, odd samples, has the gain of 1 plus beta. So we previously also looked at this kind of sequence So it can be represented by the addition of a DC entity, and that DC entity will be just the average value of these two. So it will be a DC, like we looked in the case of offset. So it's similar. And along with that, we will also get a tone with a frequency of fs by 2, or basically omega equals to pi. So these two, like we can realize this thing with the addition of DC as well as the tone. So we realized it in the case of a non-ideality due to offset. Yeah, so that's the same thing. So over here, the main ideal expected discrete output is getting multiplied by a tone, and we also are having a DC quantity. So now we will go, or we will move to a non-ideality, uh, which is time skewing. So while talking about time skewing, so ideally the samples we expect to get from the upper channel, right? So upper channel, which basically means uh, I'm talking about this upper channel. So this is upper channel, this is lower channel. This, so from this top channel we're expecting even samples, and from this lower channel we are expecting odd samples. So the even samples which we are expecting is basically x of 0, x of 2t, x of 4t, and so on. And from lower channel we are expecting x of t, x of 3t, x of 5t. But in reality, so basically what we are expecting is this system. So we have the system, we are providing x of t, we are sampling this x of t over here. So we are in the back of the mind, we are thinking that this is happening simultaneously, right? These two parallel operations are happening simultaneously. So this means they are operating at same instance of time. And then when we add them, so this is also happening at same instance of time. But there might be a possibility, or there is a non-ideality, where this channel and this channel has some kind of time skewing. So basically that's what time skewing is. So they might vary from the instant time. So in reality the time instances are slightly varied, and the time deviation is let's say it is tau. So actually what's happening is, let's say we can realize it in any of the channel. So let's say we'll realize it in lower channel. So the samples from the lower channel would be at x of t plus tau, but not x of t. Similarly, x of 3t plus tau. So tau is basically representing the time deviation at that particular instance. So then our sequence or the samples will be like this, including the tau, which is a time deviation. And when we switch the signals from top and lower channels, so basically this is what we are doing, right? So we are stitching the signals together. So when we stitch those signals together in order to get the output, so then together we will get x of 0, x of t plus tau, x of 2t, x of 3t plus tau, x of 4t, and so on. So clearly, this is not the desired sequence or the spectrum we expected, right? What we expected was like this: x of 0, x of t, x of 2t, x of 3t. But then we are getting a error due to time skewing. And that error can be evaluated by the actual sequence minus the ideal expected sequence. So then, according to the Taylor series, for a very small amount of tau, so basically, if we assume that the amount of time deviation is very small, so for a very small amount of tau, x of t plus tau is nothing but x of t plus tau multiplied by dx by dt at the value t equals to t. So then we can realize our x of t plus tau as this value. So when we talk about error, so x of 0 minus x of 0 gives us 0, but x of t plus tau minus x of t So that's what we are talking about. X of t plus tau is basically x of t plus this entity minus x of t. So x of t will get cancelled, and we will be left with this quantity, and where t is corresponding to capital T. But then we'll again get 0, then we'll again get t corresponding to 3t, then for 5t, and these zeros. So I hope the spectrum of the error is represented mathematically like this. So I hope you understood the error. So let's say this quantity tau dx by dt at t equals to kt, where k is an integer, is represented by x prime of kt. Will represent it like this, x prime of kt. So then the error will look like 0 tau of x prime t, 0 tau of x prime 3t, again 0 tau of x prime 5t. So then our error will look like this. So we can say that the error will have more and more significant impact or the effect when we'll have higher and higher input frequency. How? So the error is nothing but it is depending on the time, right? So time is inversely proportional to the frequency, like frequency is 1 by time. So if the time or the deviation error will increase, so it will have more effect if we have higher frequencies. So and also the error is depending on dx by dt as well, right? So from these things we can say that when we like the more we move to higher frequencies inputs, the more effect or the impact will be there due to the error. So the spectrum of the sequence. So basically, what we are doing is we have x of t, and then we have a d by dt. So we have a differentiator over here in order to achieve this, and then we are sampling at the rate of 2t, and at this point, the Fourier transform of the signal will be j2 pi f x of f. So this is corresponding to tau. And when we have done so what basically we are doing over here is we are having x of t, and we have a gain factor, and analog like in analog filter bank. So basically this is represented, this part of our representation is given by analog filter bank, so we'll talk about it. So we have a gain factor of 1 in the channel which responds or corresponds to even samples, but for odd samples we have a delay, right? Like this is corresponding to a delay when we talk about time skewing. So it corresponds to e to the power j2 pi f of t. Then we sample at 2t, then we upscale, and again we have a box whose transfer function is 1. So this is a DC filter bank, and we are introducing a 0 in order to get a time delay. So again, we are adding up this signal, or basically stitching up this two channels in order to get a discrete sample. So I think this is all about time skewing, and now this from this point onwards we will talk about, like until now we also already talked about two channels, right? But from this point onwards we'll talk about n channels. So we will derive mathematically for n channels. So for this video I think that's all, and from next video onwards we will start with n channels. So yes, if you guys have any doubt, please let me know.
Rishi?
Yeah, please.
Yeah. So can you tell me how you derive this? The spectrum of the sequence will be like x of t divided. Yeah.
This one.
Yeah. The below block diagram.
This one.
About that.
This.
Yes.
So like this is very in layman terms. So
Hmm.
when we talk about the delay or the error, so this is just for the error when we try to derive the spectrum for error, not for the actual one or not for the ideal one. but this is where, like when we talk about the error, so at that point we have something which corresponds to this value and the time delay itself, because we have x of t, right? Ideally we have x of t at the input. So according to the Taylor series, for a very small value of tau, so we are considering x of t plus tau. So we are considering the odd sample. So x of t plus tau is nothing but x of t plus the tau itself times the uh,
Yeah.
differentiator, right? So to represent this differentiator, so we have represented a box of differentiator, and that's how we then when we sample. So at this point, so whenever we have a time delay, so the delay is given by this quantity. So that's how we just represent it in the block diagram. That's all.
Okay.
But basically, this concept is called time skewing. So
Mm.
uh, you understood what do I mean by time skewing, right?
Yeah, I got